Hi, everybody. I'm Nathan, and I'll be going over work my group has done on parallel algorithms for sampling arborescences in parallel. Okay, so our story sort of begins when we want to look at these sort of, I guess, the most basic questions you can ask in computer science when it comes to, you're given an object and you want to query about it. So let's say we have a graph and we wanted to know about, I don't know, perfect matchings, for example. Sort of the level 0 question you can ask is, can we find one? Does one exist? But the two sort of harder questions are counting, so how many perfect matchings are there, and sampling, so can we produce one at random? And for a large class of problems, these two tasks of counting and sampling are essentially equivalent up to a polynomial time reduction. But once we restrict our computation a bit further and the picture gets a bit more messy. Specifically, if we wish to look at parallel algorithms, so we're going to be working in like a PRAM model. So we have all these different processors and they're communicating via some shared memory. Then just as sort of polynomial time algorithms are the gold standard when it comes to sequential algorithms, there's something we can define as Nick's class or NC, where we have polynomially many processors and the ultimate runtime though must be polylog n. So the total work is still polynomial, but it must be heavily parallelizable work. And then sort of adjacent to NC is RNC, which is just same context of polynomially many processors and polylog runtime, but we're just allowed access to randomness now. So I guess sort of returning to this disparity between counting and sampling algorithms, there's a whole bunch of combinatorial structures which can be counted exactly via determinants, spanning trees, arborescences, perfect matchings, etc. And in general, determinants and sort of linear algebra is all doable in NC. There exists fast algorithms to do this. In other words, we always have all these structures where exact counting can be done very efficiently in parallel. However, this reduction in sequential algorithms was some polynomial time sequential reduction. And in the context of parallel algorithms, even though we have exact counting, whether or not we have efficient parallel sampling algorithms is still unknown. And so our work will be focusing on one of these tasks, specifically arborescences, which are this sort of natural generalization of spanning trees where edges form a spanning tree, and in addition, you pick one vertex to be a root, and every other vertex aside from the root must have one incoming edge. And arborescences are one of these structures which can be exactly counted via some determinant computations. And what we show is that there's an efficient algorithm to sample arborescences from a weighted digraph in parallel, so specifically in RNC. And we sample these arborescences with a probability proportional to the product of the edge weights. So to do this, we use sort of two basic building blocks. The first of which is the Aldous-Broder algorithm, which has been used a lot in sequential algorithms to develop sequential algorithms for arborescence or spanning tree sampling. And what this algorithm tells us is that to do this task of sampling, once we fix a root, all we have to do is sort of run a random walk and record each edge which visits vertex which has yet to be visited. And by the time every vertex has been visited, we'll be left with some arborescence. And it turns out that this arborescence will be distributed exactly as the distribution we described before, where something is sampled with probability proportional to its weight. And there's a few sort of small caveats or fine print when it comes to Aldous-Broder. The graph has to be strongly connected, and the starting vertex forms the root. And of course, this random walk turns out to need to be time reversed. But these are kind of small details which are not too important because, I don't know, this is really cool. We can reduce this task of random sampling of arborescences to simulating a random walk. And good job, everybody. We have reduced a seemingly sequential task to another sequential task. But I guess here comes our second building block, where work by Tang has shown that we can actually efficiently simulate these random walks in parallel. So he told us that basically to generate a polynomially long transcript, you can do this using polynomially many processors in polylog time. So as long as L is polynomial, this random walk transcript can be generated in NC. Now the general sort of intuition behind why this occurs is that sort of to simulate an entire transcript of L steps, what we can do is simulate the first L steps and the last L steps in parallel, and then sort of stitch these two transcripts together. Of course, there's one small problem, which is we don't know the starting point of the second half L over two steps. I've just somehow magically decided that we're going to simulate starting from the sort of central vertex in the graph shown. But we can overcome this by, I guess, being a bit brute force and leveraging the number of parallel processors we have. So when we simulate these last L over 2 steps of our random walk, we actually simulate these last L over 2 steps from every possible starting vertex. And then this sort of costs us polynomially many processors, which we're okay with. And then we stitch the correct sort of random walk ending to the first L over 2 steps. And so this sort of lets us break down a task into a task half its size in sort of one time step per se. And that gives us the classic sort of logarithmic runtime we wish for. So combining these two techniques, well, Tang's doubling trick already implicitly solves this problem of randomly sampling arborescences if the cover time of the graph is polynomial, because then we can sort of just use Tang's trick to simulate all these steps and then extract all the first visit edges and walk away with a randomly sampled arborescence. The problem is it's very rare for the cover time of a graph to actually be polynomial. And in fact, when we consider these sort of different families of graphs, this is only guaranteed for undirected, unweighted graphs. So sort of figure 1 on the left is an undirected graph, which is weighted and has an exponential cover time, or a cover time that grows in terms of the edge weights as opposed to any sort of vertex count or sort of size of the graph. And then we also have an unweighted but directed graph to the right of that, which again has an exponential cover time. But luckily, there's this technique that's been used in a lot of the sort of Aldous-Broder sequential algorithms to speed up those algorithms, which we can also leverage in our parallel algorithm. And this idea is shortcutting. So I guess what is the key idea of shortcutting? The key idea is that when we talk about Aldous-Broder's algorithm, normally say we simulate this entire walk, but what we really care about is just the first edges that visit each vertex. So in other words, if we, let's say we simulate our walk, we're starting at E and we're sort of bouncing back and forth. Eventually, right, we don't really care about our random walk going from E to D back to E and so on and so forth anymore, because both E and D have been visited. And all we really care about is instead sort of when our random walk is in this cluster, ultimately, do we exit through edge, BD or CE? And it turns out that in general, given some vertex set, and we can fix a root. And once we fix our root, then we can compute the probabilities that this random walk ultimately exits this cluster through each of the outgoing edges. And it turns out this computation is a bunch of linear algebra. Linear algebra is very efficiently doable in parallel. So all this sort of machinery to compute the sort of fast-forwarded walk can be done efficiently in parallel. And sort of with these sort of two key tools of Aldous-Broder and this idea of shortcutting, we're ready to sort of introduce the rest of our sort of high-level algorithm before going into a bit more detail. So I guess our algorithm, we begin by reducing our graph to a strongly connected Eulerian graph. And this will make our lives much more easy. So firstly, this will sort of fill out all the fine print that Aldous-Broder needed. And this will also, the Eulerian property will allow us to sort of proceed to our second step very efficiently, which is this idea of sort of decomposing our graph into these tightly connected clusters. So sort of finding those subset of vertices, which we can leverage that sort of shortcutting insight from a few slides ago into. And once we have this sort of decomposition of our graph into clusters, we can then use sort of Tang's doubling trick to compute these transcripts of not random walks in the sense that we have a transcript of vertices and edges, but rather a transcript of jumping edges where each intermediate state is either a vertex or just some subset of some cluster that we know our walk is in and we no longer really care about any of the sort of finer details. And given these sort of transcripts we simulate, we can then sort of stitch all these transcripts together. And once we have sort of combine all these transcripts, we can ultimately have a transcript from which we can extract all first visit edges and then hopefully walk away with a randomly sampled arborescence. So moving into graph reductions, what we're going to do is we're going to try to say, given some directed graph that's weighted, we can reduce this problem to sampling arborescences with already a fixed root and making sure that the graph is strongly connected. And we do this by first sort of fixing the root of our arborescence. The Markov chain tree theorem says basically the probability that a root is an a vertex is the root is the same as a stationary distribution. Stationary distribution follows from a bunch of can be calculated with a bunch of linear algebra, so we can randomly select our root. And once we have our root, then we can then add some extra edges to our graph. And what these edges will do is ensure that our graph is strongly connected. So when we do our random walk, we're not going to get stuck and everything's going to work out nicely. And because all these edges that we're adding are outgoing edges from the root, and because the root itself by definition, any arborescence rooted at that vertex must not contain any outgoing edges. These edges we add to ensure connectedness are not going to affect the distribution of any arborescences. So sampling from this new graph is the same as sampling from the old graph. Then lastly, we can rescale edge weights to ensure this Eulerian property. So ensure that for every vertex, the sum of the weights of edges incoming and outgoing are equal. And this follows from the fact that in general, once we fix a vertex or choose any vertex, then if we take all the outgoing edges and just rescale their edge weights by some constant factor, we're not going to change the distribution of arborescences. And this is because sort of any arborescence will contain exactly one of these edges. So when we sort of scale every outgoing edge by some constant weight, the weights of every arborescence gets scaled up, and sampling is going to turn out to be the same. And so now we sort of have this Eulerian graph. And I guess the first few steps we did make sense. It's for all to not complain. But now that our graph is Eulerian, we're going to be well set on our way to computing this type of sort of clustering or hierarchical decomposition. And so I guess like what exactly do I mean when I say, we want to generate these sort of clusters of tightly connected vertices? So if we look at this graph currently up here, you can kind of imagine that when a random walk is bouncing around on this graph, they'll spend a lot of time bouncing between edges D and E, and a lot of time sort of cycling between vertices A, B, and C. So you can imagine that we can sort of identify these as the sort of tightly connected components, which, we're going to very quickly not worry about edges traversing inside of them, and instead want to know about edges that go between these two clusters. And then we can repeat this process where maybe we look at this sort of graph of A, B, and C, and then say, okay, even in this graph, we're going to spend a lot more time bouncing between A and B than sort of cycling around A, B to C. So then we can sort of decompose this again. And so we can sort of continue this decomposition until we're left with only vertices as our sort of leaf nodes in our decomposition. And once we do this, we can sort of simulate the first few incoming and outgoing edges of each cluster, stitch them together, and ultimately extract our arborescence. So then I guess here's what we want to get, but how are we going to go about getting it? So the property about Eulerian graphs is that in general, we can decompose these Eulerian graphs into at most sort of M cycles, where M is the number of edges. And when we do this, then we can imagine maybe we can try to get our decomposition by doing the following. So we sort of first decompose our graph into cycles, and then we can sort of sort these cycles by decreasing weight. Sorry, that should be decreasing. But once we have these cycles sorted, then we can take the sort of heaviest cycle and ask sort of what vertices are connected by that. In this case, in our graph, maybe our heaviest cycle here might be just the sort of loop from A to B and back. And then the vertices connected by that are going to be this set of vertices A and B. And then that sort of gives us some sort of nodes in our clustering. And then we can consider the same sort of question of when we take these two heaviest cycles, now what are the vertex sets that are connected? And if we repeat this and then sort of look at all these vertex sets computed, well, they're going to be sort of a laminar family, or each sort of vertex, each sort of set of vertices is going to be, each vertex will sort of appear in this family of sets which naturally form this type of trio clustering we see. And so this is all well and good, except for one small caveat, which is we couldn't really figure out how to decompose the graph, decompose our Eulerian graph exactly into cycles in parallel. That was a bit too hard. There's a very easy sort of sequential algorithm to do this, where you just find a cycle, sort of lower the edge weights by the minimum edge weight in that cycle, remove it, and keep going. But that again is kind of sequential. What we can do, however, is compute the sort of idea of a loose cycle decomposition, where we find a bunch of cycles where the edge weights, when we add them up, they're within some polynomial factor of the original graph. And then we can still do this process then of taking our set of loose cycles, sorting them in decreasing order, and looking at sort of the vertex sets which are connected by the heaviest cycle, the two heaviest cycles, and so on. And it turns out this will be good enough for sort of this idea of tight clustering to speed up our random walk generation. And then so given this idea of clustering, what can we do? So let's say we wanted to simulate this random walk starting at A, but we only really cared about the edges that bounced between the two sort of children of the cluster. So we only really wanted to know which edges in our random walk are going from this set of A, B, C over to D and E and back. Then we can say we're currently at A, we're in the sort of child cluster A, B, C. Because of sort of why I gestured that back in the shortcutting slide, we can compute the probabilities that we exit this cluster ultimately through BD or CE, and thus we can sort of simulate the random walk up to that sort of fast forwarding moment. So you can sort of imagine that we're generating this transcript that instead of looking like vertice, looks something like we start at A and then our random walk sort of gets a bit lost and it's somewhere in ABC. We don't know yet. We haven't really flipped the coins or figured that out exactly. But we have determined that ultimately when we exit ABC through some predetermined edge that we randomly generate. So in this case, CE. And once we're in CE, that means our random walk sort of is currently at vertex E in this cluster of DE. And ultimately, again, we'll exit through some edge, which we can randomly sort of simulate without worrying about what the random walk is doing before taking that exiting edge. And we can sort of repeat this process back and forth for some fixed L number. And then that gives us this transcript. And this process is very much analogous to simulating a normal random walk, and sort of at a very high level, Tang's doubling trick still works. So we can still sort of use polynomial poly N and L parallel processors to do this, to generate this transcript in polylog time. Of course, while we're doing this, we do this for each sort of cluster in parallel. So while we are simulating, I guess, a random walk on A, B, C, D, E, up to the resolution of the two children clusters, we do the same thing for each of the other sort of larger clusters in the graph. So we're also simulating a random walk that's currently on AB up to the resolution of its children. In this case, this is an exact random walk. When we do this for these children, we have to sort of recondition on sort of every possible starting vertex, as well as exiting vertices. For example, we condition our random walk between A and B on ultimately exiting AB, either through edge CA or AB or each of the possible outgoing edges. And yes, this is a lot of work, but ultimately this will be, if you don't think too hard, this is all going to be polynomial. And that's good enough given how much sort of parallelism we're allowed. So we generate all these transcripts for each of the possible, I guess, clusters in our decomposition, and we condition on each possible outgoing edge. And this will give us basically a big pile of transcripts in parallel that we can hopefully leverage in our next step. And so I guess here's our next step. So at sort of our highest level transcript, right, it looks something like what I've shown down below, which has a sort of very natural physical interpretation of a random walk starts at A, gets lost in ABC, ultimately exits ABC through CE, then bounces around between D and E, then ultimately exits through DB, and so on and so forth. But this is just the part that's highlighted in orange. So the part where we start at A, we bounce around in ABC, and ultimately exit through CE. That random walk was one of the ones we were simulating in parallel while we were simulating this highest level walk. And given those two transcripts, we can sort of naturally stitch these together now. And again, this is going to sort of give us a slightly higher resolution sort of random walk where we're still not looking at every single edge taken, every single vertex we visit, but we still have a slightly better idea now. And this will be distributed as if we were just simulating a random walk directly. And so then we can repeat this process again. So once we sort of splice in our slightly more refined, I guess slightly higher resolution random walk transcript, we can then again sort of look and say, okay, this part that sort of represents bouncing between A and B a lot before ultimately exiting through edge BC. Again, that's a random walk we were simulating in parallel, because this is just, again, another random walk on a cluster in our decomposition with a conditioned starting vertex and conditioned exit vertex. And so again, we can sort of splice this transcript in. And so if we were to keep on doing the splicing process, sort of, well, ultimately, if we were to sort of keep on extending every single, I guess, cluster that wasn't a vertex, I would have just described and spent the past 15 minutes of everyone's time describing this really convoluted way of sort of walking away with a normal random walk. But what we know is that we don't have to expand every single cluster, and we actively don't want to, because then we don't leverage this idea of shortcutting. So by expanding, if we choose to expand each cluster, only such that sort of we get the first L edges that sort of enter and exit each cluster, we will end up with some type of transcript that will be sort of mix of having intermediate states, which are ultimately a mix between these vertices C and then these sort of higher larger clusters. But the idea is that each of these clusters will not appear until we've already simulated a lot of the edges that a random walk would take around that cluster, and thus hopefully the sort of edges we have exactly ahead of time are good enough for extracting all first sorts of edges. So but we are going to sort of be expanding each sort of jumping edge transcript in multiple positions. So even though I sort of before was animating, sort of inserting it one at a time, you can imagine that sort of the ultimate sort of dependency tree or recursion tree looks like we have some very high level transcript, at which point we're going to expand multiple clusters with slightly more refined jumping edges of sort of the lower of the children of that cluster in our decomposition, and sort of keep on, this sort of dependency keeps on going all the way down until we are inserting sort of transcripts which are just sort of vertices. And naively, this is going to, I don't know, this looks like a mess. It is a mess. It's pretty expensive, but there are lots of things we can do to speed this up. So the first thing we can note is that while we're expanding sort of different intermediate states in one transcript, these are sort of totally independent actions. We can parallelize that away. So then we can sort of only worry about and think about the unary recursion, or like the problem of if we were only expanding the first cluster in each transcript. Now, even looking at this though, when we're expanding the first transcript and then the first transcript in that all the way down, again, the depth of this sort of tree is going to be the same as the depth of our decomposition. And in general, that decomposition, we have no sort of guarantees about how balanced that tree is. And so the depth can still be sort of order n or linear, which is a bit, it's too large since our goal is ultimately a polylog and runtime. But again, we can use a similar doubling trick like the one Tang used to speed up random walks here. And again, the classic idea is we can sort of coalesce the top half level transcripts while coalescing the bottom half level transcripts in parallel before splicing them together. So I guess sort of animating that briefly, we can imagine that we can coalesce the sort of orange transcript into the blue one while we coalesce the purple one into the green one, and then we can then coalesce the green transcript into the orange one or the blue one. And so I guess to recap, what we sort of achieved so far is this really convoluted process of generating a random walk transcript where we don't have every single vertex we have, but we have sort of the first L edges that go in and out of each cluster. And as long as L is polynomial in N, everything we've described so far can be done in RNC, or very efficiently in parallel. So I guess the last step is to say, okay, with L being polynomial in N, we can generate this transcript and we can extract all the first visit edges. But when we extract all these first visit edges, do we get the arborescence we want? And sort of to prove that with very high probability we do, what we're going to do is sort of bound this quantity, which is if you imagine a random walk on this graph, for each of the clusters, I guess when this random walk has visited every vertex in the cluster, just how many times has it sort of entered and exited the cluster? And what we show is that for each cluster, by the time that cluster is covered by a random walk, the expected number of edges which sort of go between its children is going to be at most n squared m squared. And with a bit more work, what this will ultimately tell us is that when we choose L to be some polynomial, with very high probability, our final transcript will contain all first visit edges and allow us to sort of randomly sample this arborescence. Now, I guess I am sort of waving my hands a bit and covering a lot of these small details, but I don't know, read the paper if you want to know more. And I guess sort of to recap, we've come up with this way of generating a partial transcript and using that to randomly sample an arborescence. So this is sort of a first baby step in resolving this disparity between parallel sampling and parallel counting algorithms, where we've basically taken this one problem where the counting problem can be done very efficiently in parallel, but sampling was not yet known, and well, now it's known. But I guess this disparity between parallel sampling and parallel counting still leaves a lot of open sort of problems in this direction. So I guess sort of the closely related ones would be Eulerian tours, which are very sort of intimately related to arborescences, and the best theorem actually gives a sort of polynomial time reduction from one to the other, but we don't know whether or not that reduction can be done in parallel. Another sort of very closely related question to random sampling of arborescences is, given regular matroids, can we randomly sample an independent set? And This is sort of proper mathematical generalization of arborescences and those sort of graph theoretic notions. I guess two other sort of directions we could say are very generally our work leveraged Aldous Boder's algorithm and finding a way to use that, make that very fast in parallel. And there are other sort of random walk-based algorithms to randomly sample arborescences. And specifically that's Wilson's algorithm, which can also be generalized to sort of higher dimensional graphs. And so I guess sort of looking again to try to find efficient parallel sampling algorithms in parallel, there's another direction. I guess lastly, most generally, that was that very long list of graph structures which can be counted in parallel very efficiently by taking a determinant of something. And for pretty much all those structures, parallel sampling is unknown. And with that, we're done. So thank you so much.